Hello everyone, you're welcome to Physics Experiment by Simulation. Today we shall be looking at verification of Planck's constant using the photoelectric effect simulation provided by the University of Colorado PhET Interactive Simulation Unit. My name is Professor A.S. Olayinka, and I will be taking you through the introduction, the basic theory, and a procedure that you need to be able to accomplish this task. Now, quick introduction. Photoelectric effect is one of the key experiments that supports early quantum theory. Quantum theory over the years have evolved, and it has led to several developments in various areas of human endeavor, especially in the development of quantum computers. And before the 20th century, light was considered as a wave phenomenon. However, after the development along the line of photoelectric effects, light was not considered just only as a wave phenomenon, but also as a particle. And Planck put us on the path leading out of this ticket of confusion when he theorized that light and other forms of energy comes in packets, or what we can refer to as discrete bundles, and not just a continuous stream of phenomena. Now, light in this theory is considered as a particle, which is now referred to as a photon, as we can see as we'll see in the simulation very shortly. Photoelectric effect was explained by Einstein when he conjectured that Planck's bundle of energy, that is photons, were knocking loose electrons, but only if the photons had enough energy to do the job. We can just quickly imagine a situation whereby you have a 2-year-old boy trying to knock down a footballer. That might probably be an impossible task to achieve. So for electron to be released from any material, definitely there is need to overcome the energy binding into that material. So this concept of photoelectric effects has actually given rise to a lot of development that have been currently witnessed in the development of quantum computers. This is the interface of the photoelectric effect provided by the University of Colorado PhET Simulations, and we will interact with this directly very soon. So let's just quickly go on and look at the theory behind what we're doing today. Now, the equation that supports what we're looking at today is given by Planck's hypothesis, where the energy that is causing the electron to be ejected from the metal, from the material in question, is given as hv, where h is the Planck's constant and v is a frequency, and this can further be broken down to hc over lambda, where lambda is a wavelength and c is the speed of light, which is a constant that is taken to be approximately equal to 3 × 10⁻⁸ meters per second. Now, different materials or different metals hold on to their electrons more strongly or weakly due to the atomic structure of the metals in question. So, work function for various materials varies. As we can see, platinum, for instance, has a work function of 6.35, as can be seen in this table, while cesium has the lowest out of all the one displayed here, which is 2.1 electron volt. The implication of this is this: for an electron to be released from a cesium metal, it will take lesser energy than releasing the same number of electrons from a platinum metal, because this requires more energy than a cesium metal will require. And we can see for other metals, different metals have different work function. The kinetic energy, on the other hand, refers to the actual movement of the electrons when ejected from the matter. The kinetic energy represented as Ek in this equation refers to the actual movement of the electron once ejected from the matter. And so Ek can effectively be ignored if we only provide enough energy to lose the electron from the matter, but not make it to move. In these circumstances, or in this circumstance, we can say Ek we essentially have is 0. What we're looking at is a different ballgame for you to have the electron loosed, becoming free from the bonding that is holding it to the metal structure. And it's a different ballgame to have it move or gain a kinetic energy to actually move. And so the energy, as we can see from this equation now, relating kinetic energy and work function together, that is the sum of the work function plus the kinetic energy is actually what gives us the energy, the photon energy that we have computed earlier according to Planck's equation. Okay, so we can see that E is equal to hv as we have written earlier, and it's also equal to Ek, the kinetic energy, plus phi, which is the work function. And so K is given both in joules per seconds, H, which is the Planck constant, is given in joule seconds, and the electron volt seconds. So Planck constant is 6.626 times 10 raised to power minus 34 joule seconds, or 4.14 times 10 raised to power minus 15 electron volt seconds. V is the frequency of the light. Ek is the kinetic energy I've mentioned earlier, and phi is the work function. So if a photon has enough energy, an electron will emerge with a kinetic energy equals to the difference between the photon energy and the work function. So we can write the equation above by writing that the kinetic energy is actually equal to hv minus lambda, where Ek is equal to hv minus phi, not lambda, phi. And phi is the work function, which represents the energy needed to remove the highest energy electron from the metal. Now, this is a procedure that the students are to follow to accomplish this. I haven't been able to gain access to the PhET simulation by the name Photoelectric Effect. Okay, in that simulation interface, which I will also display very shortly, the students are to follow the following procedure. Number 1, choose platinum as the material to study from the simulation window. Number 2, set the light intensity to 100%. Number 3, now vary the wavelength from 100 nanometer to 160 nanometer in steps of 10 nanometer. That is, from 100 nanometer you move to 110 nanometer, and on and on till you get to 160 nanometer, as can be seen in the table on the screen. Then the value of the current in each case is also measured and recorded in ampere. Haven't done that. We have a number of missing values in this table which is to be computed. The values to be computed are the frequency and the photon energy. From the formula earlier, the frequency is equal to C over lambda. Lambda is given here, and since lambda is given, there is need for lambda to be converted to meters before computation can proceed. Before computation can proceed, I need to convert this lambda, which is given nanometer, to meters. In order to do that one, for instance, for this, it means I will simply have 100 times 10 raised to power minus 9, and that is applicable to each and every one of the wavelengths given. So there's need to multiply the value given in nanometer by 10 raised to power minus, which is the metric value for nano. Okay, and once that is done, then there's need to plot the graph of photon energy against the frequency, which are to be computed from this table. Okay, and I haven't done that. The students are expected to take the average of the data in the table above and determine the initial kinetic energy of electron as it comes out of metal, and platinum work function as given earlier in the previous table is 6.35 electron volts. Now, to gain access to the PhET simulation, the very first link up here can give access to offline simulations, which can be downloaded. It's available both from Windows operating system and Apple operating system. So if you visit to this link, can give access to download either of the two, which can be installed on your Windows operating system or on your Linux, on your Apple operating system. And once that is done, access can be gained to this simulation offline. The following two links are links to access the photoelectric simulation that is under consideration for this experiment. This simulation, photoelectric effect simulation, is a Java simulation. It's not available in HTML5 like some other simulations. Hence, there is need to install Java SE Development Kit 8. It is required. If this is not installed, there will not be an opportunity to run this simulation. So please, this should be well noted. So in order to be able to run this simulation, before visiting these links above, these two links above, there is need to ensure Java Development Kit 8 is installed, and this last link below can give access to download the relevant Java for relevant operating system as may be applicable to various individuals. Okay, so on that note, let's meet at the other side as we play with the simulation. Thank you.